Well, welcome to Lesson 2 of our Chapter 11. This is Mrs. Hanson carrying on with you. In Chapter 11, we just really have some tips and advice and just encouragement, really, to get you proficient in planning a synthetic problem. So just, what do we consider as we approach a synthesis problem? In the last video, we talked about so many different tools. We call those reagents. And, how do I turn one functional group into another? How would I add on carbon to a carbon chain to lengthen it? Or how might I decrease the number of carbons in the carbon chain? So all of those considerations. So as we begin, 11.4, ask yourself these two questions every time you're approaching a synthesis problem. Is there a change in the carbon skeleton? Are we losing carbons? Are we gaining carbons? And how might I achieve the change in the carbon skeleton? Sometimes the answer is no, and you move on to the next question. Is there a change in the identity and or the location of the functional group? So the same two questions as we processed in our first series of lessons in video 1. We'll continue those with a few more examples and kind of give you the approach of a retrosynthesis in this video as well. So solving a synthesis problem is not a spectator sport. It's going to require you to recall all of the reactions that we've learned so far, and by working many, many examples. Proficiency comes with the multiple exposure to practice problems. Not really by sitting and memorizing the reagent charts that I provided. That's a very good first step. But by using those reagent charts to actually solve synthesis problems, that's where the proficiency will build. So let's just consider one, and I'll just do some out loud thinking, and perhaps you can follow along those two questions. So this is one of your homework. It's a skill builder question. It says, let's propose an efficient synthesis for the following transformation. Now remember our two questions. Are the carbons changing? So I want to check the carbon. Are we adding? Are we decreasing? What are we doing? Is it stay the same? And what's happening to the functional group? Do we have a different functional group? Is one disappearing and a new one appearing? We want to just get a handle on what's going on. So I'm going to just number this carbon chain. And when I do so, I want to just be sure that I can locate the functional groups as well. So I know that for nomenclature, I would start numbering here, but I'm going to choose to just count the carbon chain, not by the nomenclature rules, but just to figure out how many carbons there are. So right now I have 5 carbons, and between carbon 4 and carbon 5, we have a triple bond. Now what do we have on this side? 1, 2, 3, 4, 5, 6, 7. So now all of a sudden I see that we added 2 carbons, but notice that the functional group between carbon 4 and 5, just thinking about what happened, the functionality there is still in the same position, but it's gone from an alkyne to an alkene. So those first kind of key essential questions, is there a change in the carbon skeleton? And we said, well, yes, there is, because I started at 5 carbons with a triple bond between 4 and 5, and now I'm noticing that it's a 7 carbon chain on the product side, so we have to add 2 more carbons, and we have to change the functional group because we started with the triple bond between carbon 4 and 5. Even though it remains with that triple, in the position of 4 and 5, it's gone from triple to a double. So those are the key things you start any synthesis, is figuring out what are you starting with and where do you need to end, and go with that approach. 2 key questions. What's happening to the carbon skeleton and what happens to the functional groups? And so now all of a sudden we have the idea that we need to accomplish the following items. The triple bond must be converted to a trans alkene. And that's something that we didn't stress a moment ago, but notice that the trans position means from the pi bond, if I just imagine that I draw a line through this pi bond and the substituents are coming out, one on the top of the plane and one below the plane, that indeed is a trans configuration. Had it been a cis, we'd end up with a carbon skeleton that looked like this at position 4 and 5. And I remember learning that there are two very different reagents to produce a cis alkene. We called those poisoned catalysts, like a Lindlar's. Or if we're producing a trans, I remember the reagent had an elemental sodium and an ammonia workup. So we had to kind of think about the configuration of this double bond as well. So we have an idea of what we need to accomplish. Let's begin thinking about what we can do step by step. We can introduce 2 carbon atoms by introducing an alkylating start of the alkyne. So let's review in chapter 9, alkyne chemistry. We learned that the terminal hydrogen of an alkyne is a very acidic hydrogen. And we can take a strong base such as amide. Remember those 2 electrons in this amide? Just reviewing the how part of this. And that this electrophilic carbon, the one that is slightly positive here, well, I'm going to take that back. We're going to look out for this proton and do a proton abstraction, right? This is the one where we're just proton transfer, creating an ammonia molecule, its conjugate acid. And then remember, this bond will simply collapse. And so this first step is creating, just kind of thinking through, creating this particular compound where position 4 and 5. I don't think that's very neat. Let me write that better. 1, 2, 3, 4, 5 has now created a carb anion from step 1. So that's what we've done so far. We've created the carb anion. Now notice in step 2 what we've done is we've introduced a 2-carbon chain, and we said the leaving group, an iodine makes a wonderful leaving group because it's such a large polarizable cloud. And so here, the next part of this initiation is this negative ion forces the leaving group to leave, and we can attach on then the 2 new carbons. So what we have now is in the second step, the iodide has left. So remember that these things are existing, but we're not really writing about them, but that's where the iodine left, and that's now the new site of attachment for carbon 1, carbon 2, was that bond with the iodine. So the negative electrons on the carb anion become the new bond that's attaching to the carbon, because the electrons are going to go with the iodine. So this series is just reviewing how we approach adding 2 carbons on. So what we have now is just kind of a review of those 2 steps. First step, we create a carb anion. And that first step says this hydrogen has been removed, and we created a negative. If I take off the hydrogen, I create this. And then in the second step, we're going to add 2 carbons. That's the 2 carbons here, using an iodine as the leaving group. So a 2-step process creates the carbon skeleton that we need. We've got a 7-membered ring, a 7-membered chain with a triple bond now between carbon 4 and 5. So we've accomplished the first task. We've added 2 carbons on through an alkylation process using a terminal alkyne. Really the only way we know so far to add carbon to a chain is by using a terminal alkyne. The dissolving metal reduction that converts an alkyne to a transalkene would be the next step. So we know reduction means you're increasing the number of CH bonds. And that's exactly what we've done. We've added 2 hydrogens to create from the -ine to the -ane in the trans position. And again, I have to go back to my toolbox and remember that the sodium reduction in a workup of ammonia creates the trans configuration. Had we asked for a cis configuration, we'd have used Lindlar's catalyst. So we accomplished 2 things here. we added carbon to the carbon chain by using a terminal alkyne followed by a substrate with 2 carbons and a good leaving group like iodine. The next thing we did, we added 2 carbons as the first step. And in the second step, we changed from a triple bond to the double bond. And to do so, we used a workup of elemental sodium and ammonia. And we've accomplished then, in terms of all 3 steps, making sure that we end numbering them. That's something very critical, to make sure you number each reaction in a multiple step synthesis. Merely listing all the reagents together is not sufficient. And instead, we have to list step 1, step 2, step 3 to accomplish all of the transformations. And it's so critical that you can think through what is each step accomplishing. I have to remember that the first step accomplishes the production of a negative ion. We deprotonate that hydrogen here and create a negative ion. And that then serves as the nucleophile that goes seeking the ETI. And remember, ET is ethyl, and iodine is a great leaving group. And so now we can see that the attack here is on this electrophilic carbon, and in that way, we've lengthened the bond by 2 carbons. That was our first step. Second step, adding the 2 carbons. Third step, transforming 1, 2, 3, 4, 5, 6, 7. Between carbon 4 and 5, we produced the trans configuration of an alkene. I have to be able to envision what each one of these reagents accomplishes in a long list on an arrow. So that's your practice. 11.7 is going to give you an opportunity to kind of think through synthesis problems. And again, it's not a spectator sport. The only way to really get proficient is for you to go try these now. And when we think about approaching a synthesis, what I like to do, and many organic chemists, they think about it backwards. So the next tip I'm going to give you is called retrosynthetic analysis. Approaching a synthesis problem by really thinking about last step, how do I accomplish it, and then back up to the previous step and back up to the previous step. It means this approach, we solve the problem for the reaction in the reverse order. So we begin by solving the last step in the synthesis first. And just still ask yourself the same 2 questions. Is the carbon skeleton changing? And is the functional group changing and or moving? Same key questions, but instead I have this reactant and I have this long arrow and I'm given a product. Instead of beginning here and say, what can I do, what can I do, what can I do, start here and just go back. How can I change this into this? How can I change this into this? And I just keep working back until I arrive at my initial reactant. It's much more effective in working backwards, and let's kind of show that with some specific examples. So as a practice, let's perform a retrosynthetic analysis for the following synthesis. All right, same 2 questions. What's happening with the carbons? Are we adding, subtracting, or are they staying the same? And what's happening to the functional groups? Are they changing? Are they moving? We want to keep track of those 2 key questions. How many carbons do we start with? How many do we end with? And what happens to the functional group? So I'm going to just count the number of carbons. I have 1, 2, 3, 4 carbons in the chain with 2 methyl groups coming off at carbon number 2. Here I have 1, 2, 3, 4 carbons and 2 methyl groups coming off of carbon number 2. So we've noted that the number of carbons has not changed. So we don't need to worry about adding or subtracting carbons. Carbons look like they stayed the same, but what has changed is the functionality. At carbon 4, we see that we have an alcohol. My hand touches the bottom of the screen and it comes up. And then over here now, between carbon 3 and 4, there's an alkyne. So we see that the carbon chain remains same, but the functionality is indeed different. The alcohol converts to an alkyne, but the position is unchanged. So let's think about what we need to do to convert an alcohol into an alkyne, but by thinking backwards. In other words, how do I make an alkyne? That's my first question to myself. Thinking about if this is the structure I need to end with. Here's the two methyls coming out. Carbon 1, 2, 3, 4. My question is, what do we need to make this? So as I think backwards, I'm just thinking like, what is in this box that would give me a terminal alkyne? So go into your toolbox, and this is what we think about. How do I make a triple bond? And those are the kind of the questions then that we have to ask ourselves. What reactions do we know that can be used to make an alkyne? That's the focus. So in a retrosynthesis, this is the very first question we work to solve. I want to end with an alkyne. What are the ways we can make it? And when I say alkyne, you have to go back into your chapter 9, that's our alkyne chapter, and look at some tools for building a triple bond. That's where the proficiency comes in, is each time you work a problem, you're forcing yourself with more repetition on all of those reagents you're working to memorize. Well, let's kind of share some of those things that we've learned. We know that to create a triple bond, we have to do an elimination, right? A minus HBr, for instance. And to do so, we need to have some bromine or chlorine, but bromine is the easiest to put across the bonds in the most controllable way. And that the vicinal dihalide is the only way we really know how to make a triple bond. So here's carbon 3 and 4, just to remind ourselves what the molecule is that we're working with. To create a triple bond in a two-step process, we need to eliminate HBr. That would get us to an alkene. And in the next step, we eliminate the second HBr, and we end up with an alkyne. So we're looking to eliminate. What reagents have we learned that can take a vicinal dihalide, that's carbons that are on carbon 3 and 4, not on the same carbon, that would be geminal, but on two different carbons involved in the bond. So this would be geminal. This also is geminal. And the term here is vicinal. Spelled it wrong. There we go. So what tools do we know to do that? And this again, go back and find those tools that you're working to practice with. And here's what we find. With this vicinal dihalide in excess amounts of sodium amide, followed by a water workup, we create a terminal alkyne. Think through what we just said. Here's your bromines. And remember, the sodium is just simply a spectator. So here's your NH2. Alrighty. And so what we're looking at is trying to go through these carbons, right? Those carbons, and going through and creating one step at a time the negative ion. And so this very strong base is going to attack the electrophilic carbon and forcing the leaving group to leave. And you can go through and kind of decide, oh, we've made a negative ion, and then we take off an HBr each time, and we said that will go on and on and on until we add the water in the last step. And just remember, the water's purpose was to add on a proton, to get rid of the negative ion. And go back and review your chapter 9 if that mechanism isn't familiar with you. It's time to stop and just put that into cement. When I add excess sodium amide, what I'm doing is elimination. An excess amount says I'm going to take both of these HBRs. Remember, H and Br come off. There's an HBr, that would be your double bond. Here's an HBr, that would be your triple bond. To stop that then, to put the proton back on the end, we add the water. All right, so that's our first step. That's what we said. How do I accomplish going from an alkyne, and what I said is to the vicinal dihalide. And remember this little arrow here, it says can be made from. Alrighty, so thinking backwards, the triple bond can be made from the dibromide, and the tools that do that are sodium amide, excess amounts to remove both HBRs, and the water to put the proton back on. So now what do we think of? I'm ready to start thinking about this step. What can I do to put 2 bromines across carbon 3 and 4? See the pattern? I started with this and I said, how can I make it? How can I take something and convert it into an alkyne? And that brought me into my chapter 9 chemistry, and we've decided that I can turn a dihalide into an alkyne by using these reagents, sodium amide and water. Now, how can I make a vicinal dihalide? What can I do to get that accomplished? And that's where you have to challenge yourself to think about your toolbox. Well, I know that it's going to be made from a bromine molecule. We're going to add an addition reaction to an alkene. So to create the dihalide, we need a double bond so that I can add across the double bond. I'm thinking about addition here, not elimination as the easier step. So remember, these are just 2 general patterns, your addition or elimination. In the previous slide, this was an elimination. And now we go to create the dibromide. We need to add bromine into the workup, so we call that an addition. And how we accomplish adding 2 bromine to a molecule is through the workup of an alkene. Now, how do I get the bromine in there? Well, we understand I would need a molecular bromine to add 2 bromines across the double bond. And so I'm working backwards and deciding what do I need now on that arrow. I also want to emphasize that the non-polar solvent is also a critical choice when we're brominating an alkene, because the non-polar solvent guarantees that both of these bromines will be added across the double bond, right? So both of these positions become brominated. If I had used a polar solvent, and the general choice there is water, we would have ended up kind of thinking through, oops, I'll draw that in the same pattern. Where this double bond is, we would have ended up with the position of the bromine first and an alcohol second. So with the double bond addition and a polar solvent, the second bromine stands no chance of adding, because remember, this actually adds as a protonated water molecule, and then the next step you extract the proton off. But we end up with an alcohol and a bromine when we have a polar solvent. So critical that we have a non-polar solvent, so both bromines will indeed add. Working backwards. Step 1, how do we make an alkyne? We decided we could make it through 2 elimination steps from a dihalide. To make the dihalide, we knew that we needed an alkene, and we could brominate in a non-polar solvent. With one more step to think about. How do I make the alkene from a primary alcohol? How do I get a double bond between carbon 3 and 4 on this particular carbon chain? And do you notice then I want to remove an OH? I can think about an elimination step where I'm going to dehydrate, right? Take water out. With this step, we need to convert the alcohol to a tosylate and then eliminate with a non-nucleophilic base. If I'm asking the alcohol to leave, we have discussed numerous times about looking at an opportunity to make it a better leaving group. So step 1 is just really converting that alcohol, which is a poor leaving group, into a better leaving group using tosylate chlorine and a pyridine workup. And then going back to your toolbox with a non-nucleophilic base. Now watch me, I'm going to scroll way up here to remind you where I'm pulling these reagents from. A non-nucleophilic base. These are those bases that we memorized or looking to remember way back from our very beginning lesson, way back from chapter 7. We need a weak nucleophilic base. And that reason is because we want to promote elimination and not substitution. So that's the key of picking the reagent here, way back in that review. As I decide what base to use to accomplish this, what we end up looking at is this particular chart for our selections. So this is the highlight that creates our answer in this particular step. DBU, DBN accomplishes the alkene, then I brominate, then I eliminate HBr twice to force an alkyne to be produced. So overall, this is what we've decided. We had a multi-step synthesis. We started working backwards. We started down here with steps 4 and 5, working up with a sodiumide and a water molecule. That would change the bromines into a triple bond. We then had to go through and find a appropriate base and tosylate compound to eliminate the alcohol. Now notice that there are multiple choices here for abstracting that, and just kind of emphasize there are more than one right answer. Notice that the base that's selected on this slide is not matching the same base here, and that's okay because there's multiple correct answers. With this big bulky base and a primary alkyl halide, we'll accomplish the same thing. We create a better leaving group, we use a big bulky base or a very weak nucleophilic base, and we can abstract off that leaving group and form an alkene. So steps 1 and 2 are used to take off the alcohol and make the double bond. Steps 3, add the bromine across in a nonpolar solvent, and steps 4 and 5, remove those bromines to create the alkyne. So remember, important to number them. I recommend thinking backwards as you tackle these problems. And to ensure that it's correct, work out each reaction and make sure it's regio and stereo selective. For example, with our trans configuration, I had to pick the correct reagent to end with trans, not cis. We want to make sure we're considering, are we adding Markovnikov or anti-Markovnikov? Do we need a Zaitsev elimination or a Hoffman elimination? And selecting the correct tools helps me get there all through those questions. So the best advice is to build a molecule. You must choose from the right tools for the job. And it's helpful to organize the reactions as you learn them into 2 sets of equations. Reactions that alter the carbon skeleton. Are we adding carbon? Are we removing carbon? Those are a series of reagents that accomplish the first task. Then in a different toolbox, place the reagents that alter functional groups. If you keep track of your reagent list as those that alter carbon chains or those that change functional groups, you'll end up finding those reagents faster to accomplish the tasks. So if you're adding or subtracting carbon, what are those reagents that do that? Are you changing functional groups? What are those reagents that do that, and how do they do that? And that's going to be your key in organizing your synthesis. And again, the last note I'll say is practice, because nothing will create proficiency other than extreme practice and over and over, the repetition of looking up your tools, your reagents, starts to solidify your synthesis scheme. I wish you luck, and I'll see you in class.